Okay, welcome back. So in the previous topic we have discussed about the floating bodies, and now let us continue with this remaining concepts of these floating bodies. So let us discuss relative atmospheric pressure. As already we know that the atmosphere extends up to about 1600 kilometers. As already we know, the earth is surrounded by an atmosphere and it is almost 1600 kilometers from the earth's surface. And atmospheric pressure is the force exerted by the air per unit area on the earth's surface. So what we call it is atmospheric pressure means the force exerted by the air, that is called atmosphere, per unit area. And as already we know, the standard atmospheric pressure is always taken as per the sea level, which is equal to 1 atmosphere ATM, which is equal to 0.76 mHg, which is equal to 10 power 5 pascals. Means generally already we discussed it is measured in pascals. So the value is taken as a 10 power 5 pascals, and we can also consider which is nothing but 0.76, where 1 atm is nothing but taken as 0.76 as we said, into 13,600 into 9.8, which is 10 power 5 pascals. Next, as already we know, to measure this atmospheric pressure we use the device called as barometer. And here you can see a simple barometer which is called as a Torselin barometer or a mercury barometer, which is the device which is used for measuring the atmospheric pressure in the beginning of our applications. Now let us see. The barometer was invented by Torselin in 1643. That's why it is also called as Torselin barometer, and which is having a mercury used to measure the pressure. And formula to finding the mercury, that is atmospheric pressure, P is equal to P0 plus H rho G, where P0 is taken as a pressure. Now coming to how to design or how to construct a simple mercury barometer, which already we have seen in the previous slide. Further, we take a glass tube which is containing 1 meter long. So this you can see, this is a 1 meter long glass tube, or we can also say a narrow tube which is closed at one end, and it is filled with pure mercury without air bubbles. So this is the mercury which is filled, which we can see here. This is the mercury. After filling with mercury, to remove the air bubbles, just we keep our thumb finger on the top of the open tube and just we rinse up and down, so that if any air column is there, that is called air bubbles are there, they will come upside. Then that remaining part also we fill with a mercury. After filling with this mercury, we take a one glass tube or we take a one beaker. Sometimes we say we take a porcelain dish which contains a mercury, and we insert this tube invertedly into that mercury tube, that is into a mercury mercury tub. Once we keep inverted position, we will notice that slowly the mercury falls down from the tube, and which occupies the jar which we have taken in consideration. So this tube, after some time, you will see that the level of the mercury will be at a fixed position, means it will be stable position, where we call that is the mercury height. Now you can see, if you observe this height, it will be 760 mm, means 76 centimeters height. So we say that the pressure exerted by this atmosphere is 76 centimeters of mercury column. And this air which is occupied, where we say which is called a vacuum, this vacuum is called Torselin vacuum. So it is given by the name of the scientist who discovered this. So this is about a simple method to construct a mercury barometer or a Torselin barometer. Now let us discuss about buoyantic force. What is buoyantic force? How this buoyantic force will be exerted? So let us see about buoyantic force. An object immersed in a liquid experiences an upward force, which we call it as a buoyantic force, or it is also called upward thrust. As already we know, the buoyantic force makes an object weightless in a liquid compared to air, means its weight will be less than the weight in air. So which is called as nothing but it is losing some weight. Here you can see the ship which is traveling can identify that it is acting some buoyantic force by the water in the ocean or in rivers. Now what are the causes of buoyantic forces? First one, as already we know, liquids exerts pressure in all directions, and also it pressure increases with depth. That you can see here. The force on the bottom of the object at a greater depth is higher than on the top at a lesser depth. Means here if you see the force exerted of this buoyantic force, which is this is called greater depth and this is called lesser depth. So here the buoyantic force is more and here the buoyantic force is less. These differences in the forces creates a net upward buoyantic force. Means these both the differences what we are taking will make the net force to be acting on this object to have a buoyantic force. The upward force makes the object to feel lighter. Means what happening? Due to this upward force, the weight of the object is less than its actual weight, or it feels that it is less than its actual weight. Let us see mathematical expression of buoyantic force. So as already you know, buoyantic force means the upward force exerted by a fluid on an object which is immersed in it. Means as already I said, the liquid will act some force on object which is immersed in it to push it up. So this upward force is called buoyantic force. And we know the pressure is given by the formula H rho into G, where here we are taking the first one, pressure at first height. Means we have seen at two different heights. Here you can see this is height H1 and this is height H2. So at this height, the pressure is given as H1 into D into G, where H1 is called the height from the surface and D is the density and G is the acceleration due to gravity. And same way, pressure at depth H2 means at this depth. Means now the height is taken from the surface to here. This is called as the total height which we take. And this is H2 is greater than H1. Hence, the force of H2 will be greater than force on H1. That is, the pressure of H2 is greater than pressure at H1. So this is the formula which we see, H2 into D into G. Here we know the densities are same because we are taking the same components, and gravity is also same, so only H1 and H2 is different. So that's why this difference will give the buoyantic force. The difference of H2 and H1 will give the buoyantic force with the density and gravity. So this is the net buoyantic force we can see. So what is the buoyantic force? That is force at depth 2 minus force at depth 1, means pressure at depth 2 minus pressure at depth 1. And this also depends upon area. Means what is the area of this base or the surface of any object. And we know V into D into G, where we know base area into height is called volume. Base area into height is called volume. So volume of the object and density into gravity, where V is called volume. Why we are taking the volume means, as I said already, here A is called as the base area and H2 minus H1 is the height of that object. So this is the mathematical expression for buoyantic force. Then let us see what are the factors affecting the buoyantic force. So different factors will affect, as already we said, one is depth, second one density, and the third one where it is acting. So let us see. The magnitude of buoyantic force acting on an object immersed in a liquid depends upon two factors. What are the two factors? As we said, area and height. This both put together is called volume. Area and height both put together is called volume. So first it depends upon the volume of the object immersed in the liquid. So volume of the object which is immersed in the liquid. Second one, it depends upon the density of the liquid. Second one, it depends upon the density of the liquid. Why? If the density of the liquid is more, automatically the buoyantic force will also be more. So here you can see examples. P, fluid, pressure of a fluid, where we call it as density of this fluid. Due to that, the buoyantic force is acting on it. And M is the mass of the object, and G is the gravity of the what? Earth's gravitational force. So as we know that the gravitational force is always downwards and buoyantic force is upward. If these both are equal, in case gravity and buoyantic forces are equal finally, then we see the object will float on the surface of the liquid. It will what? On the surface of the liquid. In case if the gravitational force is larger, then what happens? The body will immerse into this. So these are the two factors which we can see the buoyantic forces get affected. Next, based on this, we have a one principle which is called as Archimedes principle. And already we know that this is one of the famous principle which is helped us to determine about the purity of the gold also. Okay. Archimedes principle. What it says? When an object is immersed in a fluid, it experiences an upward buoyantic force equal to the weight of the fluid displaced by it. Means how much buoyantic force it will experience means when you immerse it, it will displace some liquid, and how much liquid it is going to displace means that the mass of the liquid, one way we can say, or the weight of the liquid will be equal to the weight lost by that object. means the weight of the object in air and weight of the object in the liquid. If you check it, there is a difference. Whatever the difference is there, that same value will be observed in the liquid's weight. So that is called displaced liquid. So what is the displaced liquid? The volume of the water pushed out when an object is immersed is equal to the volume of the object. So if you compare with the volumes, it will be same, and the displaced weights will be same. Like for example, if you see, take a one overflow jar. This is called overflow jar. Initially, we take the liquid up to the outlet, that is called overflowlet. So how to take means, first you fill completely, then some liquid will flow away and it will settle at the surface of the body. It will show the surface of the outlet. Then take a one empty beaker here, empty glass jar. You take one empty glass jar. Now take the weight which you have to immerse in it, means substance solid which you have to immerse it. First keep for a spring balance or any balance. So this is indirectly, it is a spring balance only, but it is given in the shape of a circular measurement. So take the spring balance and hang the weight of that object. Then initially you will see some weight. So initially he gave its weight is 6 kgs. The initial weight is 6 kgs. Now, so keep the empty beaker on the balance, which is called as a spring balance, or here we will take a normal platform balance, and we see that it is a less weight which is showing almost 0. Now try to immerse this solid into the liquid, then you will notice that what the value will be showing 4 kilograms. So actual weight is 6 kilograms, but after immersing it shows 4 kilograms. Means the loss, means the weight lost by this is nothing but 2 kgs. The weight lost by it is called 2 kgs. So that 2 kgs you can see here due to this liquid. And when you measure the volumes, both the volumes will be same. So this is called the Archimedes principle. So now see what is the formula to find out. Force of buoyancy is equal to, as we said, volume into density into gravity, V rho G, where V is called as the volume of the immersed object and rho is the density of the liquid and G is the acceleration due to gravity. And buoyantic force is equal to weight of the displaced liquid, what we said here. Loss of weight in the liquid is nothing but weight in air minus weight in liquid. Means whatever the immersed liquid is called, loss of that is called the weight lost by the liquid due to immersion. So let us see applications of Archimedes principle. So where we use, or what are the applications which are designed based on this Archimedes principle. So as we know, Archimedes principle says that the apparent loss of the weight of a substance in water equals to the weight of the displaced liquid. Means how much weight it is losing when it is immersed into the liquid will be equal to the weight of that liquid which is displaced. So this principle helps in determining the relative density also, and the formula for relative density we know that weight of the substance in air by apparent loss of weight in water, that is W1 by W1 minus W2, where W1 is called weight of the solid in air, W2 is called weight of the solid in water, which is called as relative density. And almost we know the relative density will not have any units, it is a mean value. Now let us determine about the relative density of liquids. There we have seen about solids, now here liquids. So to know about the relative density of the liquids, directly we cannot immerse them like solids. So we take a one bottle which is called as a density bottle, and we pour the liquid which we have to find its density or its relative density into that bottle, and then we start measuring it. So for that, take a body that sinks in both water and in the liquid. So let us assume the weight of the body in air is W1 and in water is W2 and in liquid is W3. Now loss of weight in water is given as W2 minus W1, and same way loss of weight in liquid is given as W3 minus W1. Here W1 is constant in air, and relative density, that is the weight lost in a water by weight lost in that liquid, which is called as W1 minus W3 by W1 minus W2. So which is nothing but called as a relative density of that liquid. The next, based on all these things, our main theme is to study about flotation, means floating. When the objects will float, as already we know that the objects which are having the relative density is less than the liquid of that liquid will float, and we know that the density of that object should be less than the density of the liquid, then only it floats. Second case, depending upon its shape, we can make them to float. Like example, if you see iron, we say generally it sinks in water, but if the same iron, if you make like a cup, means iron sheet, if you make like a cup, then it floats in water. So let us see here. When a body is immersed in a liquid, two forces acts on it in opposite direction. One is the weight of the body acting vertically downward, means the object will act downward, and second one, the buoyantic force which we call upward thrust acting vertically upward. In this case, as already I said in the previous, if this weight of the body is more than the buoyantic force, then what happens? It sinks. If it is equal to the buoyantic force, it floats on the surface. Let us see concepts. These forces determine whether the body sinks, floats, or remains submerged. What is the meaning of sinks? If it is completely immersed into the liquid, means almost to the bottom, then we call it as sinks. Floats means at least half or some part of the object is above the surface of that liquid, and some part of the object may be immersed or totally on the surface of the object. All this comes under floats. Means we should be able to see the object on the surface of the liquid, at least a part of it or a portion of it. Then remains submerged, means in case if it is immersed into the liquid such that it is not reaching to the bottom of the surface, then we call it is submerged. So in this way we can say the three concepts. So here this is now floating. This depends upon what? Weight of the body, that is the force acting vertically downward, and this is buoyantic force acting vertically upward. So what are the laws of flotation? According to the law of flotation, the weight of the floating body is equal to the weight of the liquid displaced by the immersed part of the body. Means how much part it is immersing, only that much part is taken into consideration for flotation. Like volume of the body into density of the body is equal to volume of submerged body and the density of liquid. Then we can see that V is submerged and V of the liquid, which is equal to density of the body by density of the liquid. This shows the relationship between the densities of liquids. Next, as already we know, apparent weight of a floating body. What will be its weight? Which we call it as apparent weight. According to the principle of flotation, the weight of the floating body is equal to the weight of the liquid displaced by its submerged part. Means it will not show the total weight and it shows about the submerged part. The upthrust exerted by the liquid equals to the weight of the body, means how much force it is acting upward, means by the liquid, which depends upon this weight of the body, where we call apparent weight. So what is the apparent weight? Real weight minus upward thrust. Real weight minus upward thrust. Therefore, a floating body appears to have no weight or its apparent weight is 0. So this is about the end of our session. So let us think remaining concepts in the later on sections. So thank you.